All right, so when you first learned to graph equations, maybe in middle school, probably middle school, the first kinds of equations you graphed were lines. Do you remember that? And then you sort of broadened your horizons and you added other things to it. So after lines, you had maybe quadratics, parabolas. At some point in here, and maybe even earlier on, but maybe you didn't know the equation for it, you looked at things that were like circles. And you talked maybe even at some point before you did lines about how you move a circle up and right, down, left and right kind of things or whatever. And then you encounter other interesting things in high school. You encountered maybe some trig, for those of you who took some trig, so you encountered, like we did earlier this semester, sine and cosine curves, tangent curves, things like that. You may have also encountered in a course ellipses or hyperbolas. You may not have, it doesn't hurt if you didn't. You've also encountered for sure in an algebra course cubic graphs and exponential or logarithmic graphs. You encountered potentially something like x to the fourth or x to the fifth kind of graphs. You encountered rational equations where they had asymptotes that were both vertical asymptotes and horizontal asymptotes. So you know how to graph, or at least you've seen how to graph. Maybe you can't repeat it right now, but you've seen how to graph a lot of different things in rectangular coordinates, right? It's not just lines and circles or something like that. You've seen a lot. Well, so this is a crash course in polar coordinates, and you'll see from the get-go that a polar equation is simply an equation whose variables are polar coordinates. And you found some of them back in section 5.1. We didn't graph them, but we found them, right? So the one you found on the quiz, r equals 4, it was x squared plus y squared equals 16. You know, that kind of stuff, right? So you found some equations in the last section. And here's the note. We are going to look at 10 varieties of polar equations. Some of them have theorems or definitions associated with them, and those are in your notes. Some of them don't. And we're going to talk about how we identify or classify the equations. And very much the way that I classified the equations that you just have seen earlier in different trig or algebra or pre-calculus or whatever courses, right? You have things called exponentials, you have things called logarithms, you have things called sine curves and whatever. Those are classifications. We've got classifications for these as well. Some of them are going to be familiar to you. We're going to get some lines and we're going to get some circles. Some of them are not going to be familiar to you. You're going to get some lemniscapes and some cardioids and some others, okay? So some new ones and some old ones. You're going to get rose curves, and these are where I was briefly mentioned last time that you can get some really cool looking curves in your calculator, and so we're going to see some of that today, okay? You can graph it with your calculator, and we're also going to graph some of them by hand, though, so you can see that. All right, so the first one that we're going to look at, everybody have this written down? Okay. The first one we're going to look at is that equation r equal 4. We've seen that, right? So when r equals 4, whoops, let me move that back up. When r equals 4, we talked about how we can change that. We can square both sides, right? So this is r squared equals 16, and we can replace the r squared with x squared plus y squared. And we can recognize then that this is a circle, okay? So that's my classification, if you will. Oops. So this is a circle. It needs to have a center, and it needs to have a radius. So can anyone give me either of those pieces of information? Center is 0, 0. And if you'll remember, the way that we remember doing that, or perhaps that you would remember, is that the basic equation is x minus, I don't know why they use h and k, but h and k are the popular choices. So whatever you have inside with x squared and whatever you have inside with y squared are the center points, hk. So this is the center, hk, and it has a radius r. So in mine, I don't have anything associated with x that's quantity squared. I don't have anything associated with y that's quantity squared. So by default, my center is 0, 0. Okay? What's my radius? Well, it's 4, of course, because that is what I have on this side right here that has been squared, just like the equation generally up there. So can I draw an equation that looks like this? Well, why, sure I can. You can too. So you're going to, if you'd like, you can plot the point in the center just to kind of give yourself a reference. it might be helpful in some of the other ones where they're not centered in the middle. But we're going to go out in 4 directions. I'm sorry, yeah, out 4 units in all 4 directions. Let's say it that way. And in essence, we want to actually go through this particular point, this point, this point, and this point. Oops. And I'm going to do my best. That's not too bad, but it's pretty lopsided on the sides. Okay, so I pretend it's a circle. By definition, I'm telling you today, this is my circle. Okay. I can draw a circle in the iPad just really good, but the problem with my circle when I draw this is that my scales are now going to be off. Watch this. I don't know if I can do it this way. Let's see if I can grab it. I don't think I can. See, now my scale's off, see, because it goes through the top and the bottom, but not through the sides. Yeah, see, so it's not going to work. Okay. Anyway, you've got to imagine. Good imaginations, right? Mm-hmm. You're pretending this is a circle. Awesome. All right, so we have a circle. So anytime you end up with an equation that says r equals a number, what's it going to look like? It's going to look like a circle. And it's going to be a circle with a radius whatever r equaled. Right? This is pretty basic, okay? So the r equals ones are awesome to graph because they're really easy. If you agree, say yes. Yes. Okay, good. All right, so the next one is, well, if I know what r equals and it looks like, I should know what theta equals and what that looks like. Make sense? Sure. Okay, so here's the issue. So theta, we're going to go through why this works first. Theta is related to this idea of tangent, right? We had an equation that said tangent of theta. And we're going to take the tangent, in essence, of both sides. Okay? Now, tangent of theta, that equation that we had in the last section, said that tangent is y over x, correct? This is yes. Yes, okay, nod our heads, good. All right, what is tangent of pi thirds? This is a unit circle kind of question. It is square root 3. If you're thinking along your unit circle, you might be looking at the point or the angle pi thirds and see square root 3 over 2 and then 1/2. Right, Cole? Yeah. And then, just like Cole said, though, this is square root 3. That's what it simplifies to. So let's take that x and multiply it to the other side. Now, I know the square root of 3 makes it look funny, but pretend like that square root of 3 is just some number 7. Let's say 7. What would the equation y equals 7x look like if it were graphed? It's a line. It's just a line, right? Some of you are describing to me some things about the 7, or in this case the square root of 3. What is the square root of 3 or the 7 or the whatever number they tell you? That's the slope. So this is a line. That's my classification, okay, or the identify. When it says identify, this is a line. So it has slope that's square root 3. And if you want to give yourself a reference, that's about 1 point what? Can somebody give us a reference? Square root of 3, give me one decimal. 1.73. So let's just go with, say, 1.7. Okay? And what else do you need to know in order to graph a line? Slope's not enough. Y-intercept. Do you know what the y-intercept is? It's 0. And we can say 0, 0, because that's actually the ordered pair. But in essence, we've got a plus 0 here at the end, right? And that's where my y-intercept is located when I look at the y equal mx plus b form of an equation. Okay, I can do this. You can do it too. We're going to draw a xy axis, right, a coordinate axis. We're going to plot the point that is the y-intercept, which is 0, 0. And then I'm supposed to have a slope that's square root of 3. So, and that's about 1.7. So it means I go up 1.7 and right 1. So somewhere like that. This is not exact. Nobody said it was. I can do lines better than I can do circles. have this line. Now that should make sense because that line represents exactly, especially if you just look at quadrant 1, exactly where we would draw the angle pi thirds, right? And if pi thirds was in quadrant 1 and we went on a positive radius, we'd be up here. And if we went on a negative radius, we'd be down here in quadrant 3. It's the other part of pi thirds, okay, just with a negative radius, negative r. So anytime you see theta equals a number, you get an equation that is a line. And the line will always have 0, 0 as its y-intercept. And it will always have the angle, in this case pi thirds, as that's related to that as its slope. I know that's not the angle, it's the exact slope, but that's how it's related with the angle measure. Everybody good with that? Okay. Because things get more interesting as soon as we move away from r equals and theta equals, because now we have both r and theta within the problem. Okay, so here we have a theorem. Theorem says, let a be a non-zero real number. Then the graph of the equation, and we have two different equations. We have r sine theta equals a and r cosine theta equals a. When I have these equations, they produce either a horizontal line or a vertical line. Okay, so you guys know what those look like. And that line is always either located above or below, to the left or to the right of the pole. And what is the pole again? The origin. So we're talking about the origin. When you see word pole in polar coordinates, that means the origin from your rectangular coordinates, okay? So if we're dealing with a horizontal line, obviously it has to be either above or below the pole. And if you're dealing with a vertical line, it either has to be to the right or to the left of the pole. Everybody with me? Okay, now I'm actually going to create that so you can see why that actually works with the next equation. So take a look at an equation. It actually fits the profile, right? R sine theta equals a number. So good? Okay. Here's the deal. We had some equations back in the last section. What is r sine of theta? It's y. This is another way of writing y. Isn't it? So this is just y equals negative 2, and you know how to graph y equals negative 2 even if I never showed you that theorem, didn't you? Y equals negative 2 means I take the equation, or take the axes, and I go down 2, and I draw a horizontal line. It doesn't look very horizontal, but pretend with me for a moment. That's y equal negative 2. Now go back and let's make sure it made sense with the theorem. Did the theorem in fact say that and whatnot? So if you go back up here, this is supposed to be r sine of theta, which is section A, or letter A. Is it a horizontal line? Yeah, we drew a horizontal line. It says if a is greater than 0, we're above, but our a is negative 2. So are we below my pole? Yes. And it says absolute value of a. What is my absolute value of my negative 2? 2. So am I 2 units below the pole? Yes. Okay, so this is where this theorem is coming from. It's coming from the practical application of actually doing this. And I'm not going to do an example where I have r cosine theta, but can you imagine that it would be just the same thing? Because r cosine theta is x. And if I had x equals a number, that's a vertical line from algebra. Okay? So this one's not too bad because the cleaning up of it, whether you remember the theorem or not, it works very straightforward, yeah? It's nice. Okay. Let's do one more and then we'll stop for today. All right, here's me a theorem. So all of these equations are going to look like 2a sine theta, negative 2a sine theta, 2a cosine theta, negative 2a cosine theta. They're all circles. That's good. We know how to draw circles. The circles are all centered at 0, a, or a0, or plus or minus a negative, okay? And we're going to do an example, okay? One without all of the details of what this is so you can see that it actually will work. All right, so what I'd like to do is to take this equation, and I'm going to show you why this works. We're going to multiply both sides by r, okay? So that gives me r squared on the left and negative 4r cosine of theta on the right. From your rectangular coordinate conversions and whatnot from section 5.1, what is r squared? What is our cosine theta? X. Okay, so now back in algebra when you learned how to graph circles, okay, this has probably been a little bit for you. The thing you had to do first is to get all the x's and y's on the same side. So I'm going to move that negative 4x over here as a positive 4x, and I'm going to leave a space next to it, like so. Do you remember what the process was that you have to do next? Michael remembered. Good. You've done this recently, haven't you? Okay. Michael's taking another math class. So, yeah, we need to complete the square. Okay, so let's see if we can remember how you complete the square. Well, completing the square means you take the middle value, the value that's multiplied by x, that I just sort of darkened out way too dark. Let's do that. Now you can see it still. You take that number, you divide it by 2, and then you square it. And in this case, it happens to end up being what number? So that doesn't always happen. It's not always the same number you started with. In fact, there's only one case where it is, this one right here. Okay. So we would then take that number and we would add that number in to the blank spot that I left on purpose. But if you add a number to one side of an equation, you have to add it to the other side because this is a balance, right? We can't go just adding things at random. Now the part that's underlined needs to be factored, and the beautiful thing about completing the square is that it always factors nice. In fact, it always factors as a perfect square. That's why you created it. It factors as x plus the number that I got when I divided, this number right here. And what is 4 divided by 2? Well, it's 2. And then on the right-hand side, I have the number 4. And if you prefer, you can actually write this next step. You don't have to, but you can think about it this way. 4 is 2 squared. This is a circle. And it's a circle with the same details as on page or screen 1 when I was talking about circles before, right? With that circle. The circle's center is located with the pieces that are being squared. Now, here's what you have to remember. It's the opposite sign of what's in parentheses. So this is actually -2, 0 as my center. It's always the opposite sign. And it has to do with the way that the equation was set up. And then what's the radius? 2. So I've got a circle. My circle needs to be centered at -2, 0. Which would be right here. And it needs to have a radius of 2, which means I need to go left and right, up and down 2 from this particular point. And if I've drawn it well, it will imagine itself to be a circle. Hey, you know, that's pretty good. That's way better than my last one. And we've got a circle. Now let's take just 2 seconds to go back and look at that theorem to make sure it worked with what the theorem said. All right, so the theorem said I've got, let's see, r equals -4 cosine theta. That would be case what? A through D. Which one? Which one? D, right? Because it was cosine theta. So this is case D. So this is a circle with radius A. What is the A if the equation says -2a and my equation has a -4? What's A? 2, right? It's a 2. So it'd be centered then at -2, 0, which it is, and it has a radius of 2, just exactly like the theorem told me that it would. All right, so we'll stop there for today.